Gigawatts upon gigawatts of clean, green solar capacity is being churned out by high-tech factories all around the world. But how are solar panels actually made? Join us now on a sun-seeking sojourn as we look inside a solar panel factory. Vikram Solar is one of the few big players in the field vying for a slice of this lucrative growing market. And Vikram recently expanded its own capacity by a not insignificant 1.3 gigawatts through the opening of its new 130,000 square feet plant in Oragadam, Tamil Nadu. So let's see what goes down inside. Solar panels, also called solar modules, are made up of a number of individual solar cells. These cells can trace their origins back to simple silica sand from which silicon is extracted. Silicon is the second most abundant element found in the Earth's crust, by the way, so we're not likely to run out anytime soon. Cooked at 2000 degrees Celsius in a furnace along with a source of carbon, the raw element is then cooled to create metallurgical-grade silicon. This is usually liquefied again in order to remove remaining impurities. It's then blended with a pinch of boron and a dash of phosphorus, molded into ingots, then sliced into tiny wafers less than 0.2 millimeters thick. These wafers are then coated with silicon nitride and roughed up a bit to create texture and reduce reflectivity. Any light that bounces off a solar panel is wasted, of course. A silver paste is then applied to the front and rear surface, and pretty much that's your solar cell. At Vikram Solar's new Tamil Nadu facility, these incoming cells are visually inspected to find any obvious cracks or breakages. Cracks in the solar cells render them useless for large modular applications like solar panels. But more often than not, smaller sections of solar cell can be cut away and used for smaller, less intensive off-grid applications like solar-powered toys. After this manual visual inspection, the first of several tests under blasts of artificial sunlight to check they work is undertaken. Then a hydraulic conveyor system introduces a layer of EVA, that stands for ethylene vinyl acetate, to a flat pane of tempered glass. This EVA layer serves as an adhesive to hold fast the rows of solar cells that are automatically laid on the pane in a careful tile pattern by this 6-axis robot arm that can move 12 cells at once. The cells are connected to each other and ultimately the grid via a crisscross pattern of narrow metal fingers and fatter bus bars. These carry electrons generated from the activated cells to the tab wires and beyond, to whatever the panel will ultimately power. Engineers looking to maximize efficiency of solar cells have debated whether it's better having more bus bars. Conventional wisdom says 5 is a good upper limit because resistance is lowered, although the additional hardware inevitably shades parts of the solar cell. More fingers and bus bars can also mitigate the risk of micro cracks appearing in the cell, or at least prevent cracks spreading too far across the cell. Once all the cells are in place, another layer of EVA is added over the panel and an additional backsheet is added to encapsulate the cells and internal wiring. The next stage is called pre-lamination electroluminescence. Exploiting one curious property of photovoltaic cells, that they light up whenever a current is passed through them, inspectors can look even closer for micro cracks that might render the final panel inefficient or at worst useless. All they need to do is identify the dark spots. These micro cracks incidentally can creep in at any stage of the process. Silicon wafers are notoriously brittle and mishaps during the manufacturing or transportation phase are common. Wild fluctuations in ambient temperature can also cause irreversible damage. After this pre-lamination electroluminescence phase comes, you guessed it, lamination. An industrial laminator applies heat and vacuum pressure to the sandwich of glass, EVA, solar cells and wires, bonding everything together in a taut, weatherproof panel. Following this stage, circuit ribbons are attached to the edges and an aluminium frame placed around the edge. This aluminium frame offers the panel sturdiness, which helps prevent nasty cracks. These frames also make the panels much easier to handle and store, as well as offering some resistance to the day-to-day mechanical loads the panel will be subjected to, like heavy snow or gale force winds. Another electroluminescence test follows, and the installation of a so-called junction box on the backside of the module using strong silicon adhesive. This junction box serves not only as the collector of electricity, but its diodes ensure power only ever flows in one direction. This is important because solar panels, by their very nature, generate differing and unpredictable amounts of electricity throughout their working lives. Final testing looks for weaknesses in the panel's weatherproofing. Next, the completed panel is subjected to a final blast of artificial sunlight. And now our panel is ready to ship. Vikram Solar's shiny new Tamil Nadu facility is part of a wider drive within India to achieve what Prime Minister Narendra Modi has called his Atmanirbhar Bharat initiative. This translates pretty much to self-reliant India, the idea being to wean the subcontinent off of its dependence on foreign expertise and expensive imports. The new plant is all set up to embrace emerging technologies, for instance using artificial intelligence algorithms to spot microcracks early in the manufacturing process. As Vikram Solar's managing about sunny optimism. What do you think? Is solar still exciting? Let us know in the comments. And don't forget to subscribe for more utterly illuminating tech content.